Okay, so today we're going to start 7.6, which is counting theory. And this is day 1, and there will be 3 days of these notes mixed up with practice in between each day. Counting theory gets into kind of what we do with statistics. We're going to have some permutations, combinations. We're going to talk about something called the fundamental counting principle as well. So the first big idea here is independent events. Independent events are events that do not influence the outcome of each other. Okay? Such as if you go to a restaurant and you're going to order an appetizer, an entree, and a side, what I pick for my appetizer does not affect my entree, does not affect my side. Whatever I pick for the one doesn't choose what I pick for the other. When you have independent events, you can use something called the fundamental counting principle. And what that basically says is if I have n independent events, such as here, let's look at this first example down here. A restaurant offers 6 appetizers, 4 main dishes, and 3 desserts. How many different 3-course meals can be created? I have 3 independent events. I have my appetizers, my main dishes, my desserts. Where for each of these events, there's a certain number of ways it could happen. So for event 1, there are m ways for that to occur. So that would be 6. For event 2, there's m certain number of ways for that to occur. In that case, our main dishes are 4. And then this can go on and on for how many events you have. In our case, we have 3 events. To figure out how many different ways for all these events to occur, all you do is multiply those numbers together. So for this example, you have your apps, your main dishes, your desserts, your apps, your main, and your desserts. You had 6, 4, 3, and all you're going to do is go ahead and multiply those numbers together and find out that there are 72 different options or meals that could be created in this circumstance. So whenever you hear about the Olive Garden saying there are infinitely many different number of pastas you can create when you're there, there really isn't. The next example here, the Friend Math team won 9 plaques at regionals and state this here. The plaques are going to be hung on the wall in a row by the math office. How many different arrangements of the plaques are possible? And so in this case, our order matters. If I put, one plaque first, one different plaque second, I flip them, that's a different arrangement. So really what we're looking at is we have 9 plaques, 4, 5, 6, 7, 8, 9. Well, if I think about this could also be called the slot method sometimes. You're placing things in a different spot. Okay, so if you think about this first spot, I still have all 9 plaques to hang. So I would have 9 options. Then after I hang that one, there would only be 8 for the next spot. Then 7, 6, and each time there's less and less options for me to hang them. Okay, so if I go ahead and multiply that, you find out there are 362,880 arrangements for these plaques. So quite a bit of them. Okay. Now, this could have been done a little bit quicker if you think back to what we learned last in 7.4. This calculation right here is the same as 9 factorial. So you could actually go ahead and use 9 factorial to get that as well. Next example, suppose there's only room to hang 6 of the 9 math plaques. How many arrangements are possible? Okay, so I only get to hang 6. Well, this is going to be very similar to the last one. I still have 9 choices to hang in the first spot, 8 for the second, 7, 6, 5, 4. Okay. So it's not 9 factorial because we're getting rid of those last 3. If I multiply that together, this is 60480. So 60,480 arrangements this time. So a lot less than brute 4. And this is actually going to play into our next thing. This is what a permutation is. Okay, so this actually follows a formula. Okay, a permutation of n elements taken at r time is one of the arrangements of r elements from a set of n elements. So what we were doing in this problem is we had 9 elements and we were picking 6. Okay, so this is very, very similar to combinations. The only thing that matters now is that the order in which I have these matters. Okay, with combinations, if you picked so many, okay, it didn't matter which one I picked first. Okay, with permutations, that order does matter. So this would actually be your n, this would be your r. Okay, so you could do, if you follow that formula here, nine permutations of choosing 6 would be equal to n factorial, 9 factorial, over n minus r. It's 9 factorial over 3 factorial. And really what that does is this 3 factorial cut off the n that we had up here in this problem, and that's how we got our answer for that second one. And that's going to equal what we had up there. Now, I did post some videos the other day that shows you how to do this permutation in your calculator, and you can actually type this in and get straight to your answer. So a couple more examples. A club with 25 members is electing 4 officers, a president, a vice president, a secretary, and a treasurer. How many different ways can the 4 officers be chosen? Okay, so I have n is 25. I'm picking from 25. And then I got r. I'm selecting 4 officers. Okay, so my r is 4. And the reason that this is going to be a permutation is because it matters. Okay, imagine if we have these 4 spots. Does it make a difference if, let's say we're picking Billy. Billy's the president, and the next time around, Billy's the vice president? That's different. Okay, so there are specific spots that they are going into. So this would be 25 permutations of 4. So if you wanted to use the formula, 25 factorial over 25 minus 4, so 21 factorial, which is really ends up just being 25 times 24 times 23 times 22. So you could do it that way, or if you want to practice right now, pause this and type in to your calculator to make sure that you can do this correctly. If you're in the TI-89, it's just going to be second 5. Go to your probability and find your NPR. If you have the 84, you can find that pretty easily as well. And this turns out to be 303,600 different ways. Now, what can be a problem here is deciding what method. If we look at this one, a club with 22 members needs to choose 4 members to attend a regional conference. And how many ways can this be done? Now, it's easy to always pick out your n. So here's your n, here's your r. So we got 22, 4. Now, does it matter in the order I pick these people? No. If I pick person 1, then person 2, person 3, and then person 4, and then next time I pick person 3, 2, 1, 4, those are still the same 4 people attending the regional conference. So order does not matter. So since order does not matter, this is a combination. Okay, and one thing you're going to notice is permutation combinations. If you're doing permutations, you're going to have far more permutations than you would have combinations. And the reason for that with the combination formula, which is n factorial over r factorial, so 4 factorial, times n minus r factorial. So you're dividing by that extra part here. What this is doing is getting rid of all of those orders, like picking 4, and the ways I can mix them all up. Okay, so when I divide by that I only count that as 1. So again, if you go ahead and use your calculator to use your combinations, calculating these aren't difficult. It's really just deciding which one to use. And you see that there are only 7,315 ways to choose my 4 people to go to this event. So this is what I want to talk about here real quick is what should you use? Okay. Permutation or combination. So in how many ways can 5 oranges be chosen from a bin containing 20 oranges? Okay, so I'm talking about how many groups of 5 oranges I could pick. Okay, so the order in this case does not matter. I don't care if I pick this orange first or this orange first. It's that group of 5 that I've created. So this would be a combination. Okay. The next one, a website requires each user to select a 5-letter password in which no letter may be repeated. How many such passwords are available? Okay, well, you can't repeat any letters. So if you think about this, somebody could make theirs be A, B, C, D, E. Now, if there are 26 letters, they pick those 5. Well, that person's password would be different than someone that did B, C, D, E, A. The same 5 letters, but the order is different, and that would be a different password. Okay, so in that case, since the order does matter, we would have a permutation. And again, as I said, these can be really done quickly in your calculator, so make sure you check out those links on Schoology. And I put a little quick reference sheet down here to help you guys out with deciding which one to use. So first thing you want to make sure is, again, it's always selecting R items out of N items. So R is going to be greater or equal to or less than N. Repetitions are not allowed. Okay, what that means is, I wasn't able to pick the same letter twice. Okay, or in combinations, I couldn't pick, if I'm picking out of 20, I couldn't pick the same orange 5 times. If repetitions are allowed, okay, that's going back to using that fundamental counting principle. Okay, and so your biggest thing here is, does the order matter? Okay, things that, permutations you'd see are, schedule, what order you're doing things in. You see the word order, how are you arranging things, where'd you get elected, what office, what place in a race, where combinations is grouping people.